Okay. I'm allowed to start? Yeah. Okay, well, thanks for coming. It's special to be back, at least for one day, and see the offices and the people. I have plenty of slides. I'll go through them and let's have some interaction, okay? So I wanted to talk today about zero resources, spoken audio search. This is the task of when you have very little training data or no training data on your databases, and you still want to do something with it, okay? And I'm going to focus on the voice search part. How do you do query by example search? So this is the summary. So apart from introducing, and I'll go briefly through that, and zero resources and talking about spoken audio search, I'll talk mostly on what I've been interested in, even though it's very old technology, and I tried, me and myself and some people, we tried to push it a little forward to new days. It's based on dynamic time warping techniques, and I'll talk about this algorithm, which is actually the first time I talk about it. It's still not published. It's going to be published in Interspeech, which is an algorithm that is based on DTW, and it tries to improve the shortcomings of DTW, namely that it goes exhaustively through the data, so it's kind of slow, and it doesn't know how to treat, like you cannot treat data that has been pre-indexed in databases and stuff. I'll put this into the task of query by example spoken detection, which is the audio search task. I'll give you some examples and just conclusions. So to start with the zero resources, you know much better than me about the zero resources case with the Mediaeval program, but just this is an introduction. I mean, there is tons of languages in the world. These are the language groups that are in the world, but in terms of languages, there is more than 6,500, according to Wikipedia at least. From those, more than 2,000 have less than 1,000 speakers. So this actually makes us think, okay, have we actually ever done some ASR or something on these languages? I probably not. So what people have been working mostly is on these top languages, right? And maybe a few more. But you can see that the curve goes down pretty fast, and this is kind of the exponential thing that of many like you can see it in many areas where the long tail effect of the things, it's things that cumulatively they are important, but by themselves they are very, very little number of speakers. So as an example, and this is an example because I use it in the tests, in Africa, even though I think there's 6, 2, 4, 6, 8. There is 8 main languages that are used. These are the colonizers' languages that are used officially in most of the countries. There is plenty of languages spoken all over Africa. Actually, I don't know if it's right, but I found on the web that more than 2,000 languages or languages and their dialects are spoken everywhere. So building things for all those languages is totally impossible, and there is no money for that. And this is kind of my NGO. Oh, the slide is very bad. My NGO type of slide saying, okay, do we want to do something for that? We don't have money for that. It's not interesting economically, but in order to be able to do something on that, we need zero resources technologies that we don't need training data. We just need the audio data, and we work with it. And this is a definition of what I mean with zero resources. We don't have transcribed training data, dictionaries. Sometimes we don't even have the knowledge of the linguistic structure. We don't know anything about the language. So it's something that sounds like a language. We don't even know what language it is. So how can we do something with it? I mean, assume we have the actual recordings. We have recordings of a language a few hours or whatever. Can we do something with it? Well, this is what we're trying to address with the zero resources task. And this is just 4 small things that have been tried in zero resources. The first one is the one I'm going to speak a little bit on application today in the spoken audio search or query by example. Same thing, it's you give an audio query, so you say a word, see where this word is spoken, okay? So, and this is used, I'll introduce a little later. The task we are playing with was introduced by IBM with their web based or a spoken web task or spoken web project that try to give access to people in rural India to information by just speaking what they wanted. Automatic term discovery is just trying to discover repetitions in your acoustics, in your acoustic database, trying to just structure their data somehow, trying to find what's repeating, what's in there. There is people doing interesting things with this in France, trying to see how infants are learning a language by just looking at, trying to correlate, okay, you know, if whenever this is heard, this happens, I mean, trying to correlate these things. Topic identification, so if we do have some documents that we know what they belong to, or what topic they belong to, by comparison of these documents at acoustic level, we can try to identify the topics. Or spoken document summarization. We did something like that with a student a couple years ago, trying to do kind of these word clouds, but in audio, try to summarize, have a list of the 10 most spoken words or the 100 or 20 most spoken words, play them out, and so you can kind of get a feeling of what's said in the audio. Okay, of course this is all limited, because you don't have the text or you don't have access to the ASR, but still I think it's interesting. So spoken audio search, I've already said that, and this is a hey, and there's two guys trying to find something there. It's
gonna happen next.
So spoken audio search is also known as query by example. Spoken term detection is a very long name, and it's, as I said, it's given a spoken query. We find the instances, which I call the. I never know how to define it. I say the lexical instances. So like if you say chair several times, you want to find all the times you said chair, right? On the spoken documents. And this is similar, it's the same idea of the spoken term detection. There was an evaluation 2006, but in this case we don't go from text, or even, you know, the Mediaeval evaluations, right? We don't go from text, we go from audio. And this audio that is spoken in the query and the audio that is in the documents is different speakers, sometimes different acoustic conditions. And you would say, okay, that's fine. We do some kind of speaker artist training, or you know, compensate for the speaker differences. It's not that difficult because the queries are just 0.5 seconds or 1 second, so it's very small data to work with.
Quick question.
Yes.
Before I go much further, this has always been really confusing to me. Well, what is keyword search, and how's that different from, or at least what we do in Babel, how's that different from spoken term detection?
It's not spoken.
Yeah, it's.
We get the keywords as text. They get the keywords as audio.
Okay, so the queries are spoken. Okay, so what we do is spoken term. It's STD as well. Or no?
It's STD, yeah. We do query by example STD.
No, but Babel is not, because we don't have the audio of the queries. Right.
No, but you have the audio of the. So spoken term detection, as it is defined, is you have the audio corpus.
Yeah.
And then the queries are text.
Spoken term detection, but not query by example.
Exactly.
So Babel actually does spoken term detection, but we call it keyword search. But this is query by example, spoken term detection,
yes.
Or spoken audio search.
Yes.
Okay.
Yes.
I guess that makes sense.
Yeah, spoken term detection.
That the query and
It's a great acronym.
thing you're searching are the same language?
Well, yeah. If you wanna find something, we do search acoustically. So if the acoustics sound the same, we would go with it. I mean, if you say chair in another language, but you also say chair for that object or for some other object, it would find it as if, I mean,
You said you didn't know what language you were
exactly.
searching,
So just acoustically they sound, the queries just has to sound the same. So okay, so you know more than me. What we can do here is just we can go just for the audio, pattern based, and I'm going to talk about this later. If we add the language, the spoken language, we build acoustic models with the spoken language. We can go with lattice based or string matching techniques. And if we add to it language models and a little bit more training, I don't know, a lot of knowledge, we can go for word-based, ASR, and then do work-based. We'll forget about this part. This is, for us, is impossible. I mean, in low resources, and even for Babel, like, you cannot really build this. Let's focus on these two here. I'll just introduce this a little bit, and then I'll focus on the pattern-based. So I'm saying that because I'm gonna show results mostly that coming from the Mediaeval spoken web search evaluation. The Mediaeval evaluation is what? What's that?
We always thought it was medieval.
I thought it was medieval, but no, it's medieval.
Mediaeval, yes. Well, if you want to have that A and that E, you can put it together, the thing. So Marta Larsson started it in 2008 comes from the Videoclev evaluations, and since I think 2010, 2011 is called Mediaeval. It's focused on they do a lot of video, a lot of some audio, multimodal. Actually, Gerald, not here, but he's participated and proposed a couple tasks in the past. And well, within this framework, the spoken web search, and I'll go a little bit on why it's called this way. Task it started in 2011. That comes from the fact that IBM India proposed the task initially. They are interested. They have these. I'll go to the next slide. This is kind of the example. So in rural India, they had a big push trying to push this project to build small ASR systems or something technology that users could call and get information, and could record their own voice websites or voice sites, and then other people could search on those, and kind of this way to exchange communications without having to have a smartphone or internet access. Just with their feature phone have to have access to it. So the sounds, if we have sound, the kind of recordings you get.
We're going to be doing that.
There's even background noises, right? So this is kind of the audio we got in 2011. It was very, very hard. And
What dialects? What
so I'll go into that. I don't remember them by heart. I have them in some slide. But basically, so they put together a few hours of this data. They put together some queries, and then we were trying to match, okay, to find where the queries were spoken. And basically, the task, how it goes, and it still goes that way. Participants get some development data, get some queries. After 1 or 2 months, they get the test data and maybe some tests, some more search material, and then they have to turn in it's standard NIST evaluation. They turn in their XMLs or RTTMs outputs, right? Let's see. So a little bit of history of the spoken web search. 2011, we had 5 finishing participants with 4 Indian languages. 2012, we had 9 finishing participants with 4 African languages. And this year, it's going to happen in October. So far, I just updated this morning because we just have one very late participant signing up, Georgia Tech. I might have, couldn't say that anyway. We have 18 registered participants and 9 languages. And I'll just discuss briefly what these languages are. So I'm gonna
causation correlation slide, by the way.
The what?
The graph there.
Exactly. Yeah. Well.
They're so heavily correlated.
So.
He had a graph of the size of the database and the number of participants.
Yeah, here.
It was completely correlated.
It's like, participants and
wondering what the causality
number of minutes. So no, money is 0. There's zero money in this thing.
So it is.
Yeah, that's standard. That's the base. So the languages for Indian were English, Gujarati, Hindi, and Telugu. Okay, and this 2011 we had about 2 hours, almost 3 hours of data split between dev and eval. Okay, there was search data for dev and search data for eval. In 2000. I'll skip the results page. In 2012, we switched because the Indian data was a little messy. The guys that created the Indian data were not speech people, and we had some problems there. 2012, we switched to African. Okay, not that it gets much better because the languages are totally. I have no clue what you hear things and you don't even clicks and stuff. So we had 4 languages again. Data went up because this time we had the dev set we had already 3 hours, almost 4 hours, and the eval set also 4 hours to 7 hours and a half. And in here we got a big surprise. Like some people got very good on these results. I'll just skip them, and then 2013. This is what's going to happen. And in here, I took a personal bet here. I said, okay, why don't we have to have development and eval data, search data separate? Let's just put it all together. Okay, so we have 20 hours of search corpus, and then what we did is take out from the search corpus any information about the language, any information about anything. So we just give, in the dev set, in the dev queries, we just give them the positions where these queries appear. Before, in the previous year, we were giving them all the transcription of the dev data so they could train something with it. This year, nothing. Just, we know that this places there is these queries. The rest, we don't know what language is it, we don't know anything, okay? And so anyway, we'll see, we have 9 languages. So we have 4 African languages different from last year. We have Albanian, Basque, Czech, non-native English, basically from recordings like this on Interspeech and ICASP conferences, and Romanian.
So you do have transcripts on these. You would need them.
For some of them, we do have transcripts, but we didn't give them to participants.
But you'd need transcripts of the whole search corpus to determine ground truth.
So somehow the people that created the databases or that organized this, they have either handmade transcripts or ASRs that are pretty good for that data. So so they were able to produce the ground truth where the queries appear. But that information was then stripped, and only the audio was given to participants.
So I just want to make sure I understand, so that everybody gets the search corpus, but and some dev queries,
yes,
the labels, and then for the eval, you'll be given eval queries.
Only eval queries.
You'll use the same search.
Same search, yeah.
So the eval queries will also just be start time, end time.
Yes. Well, you have to return that start time, end time.
They just give you the audio.
You just give you that.
No, but an eval query is a start time, end time, or is the eval?
No. Eval query is an audio file. Okay. It's a small audio file saying.
So the queries are not drawn from the search corpus.
No.
Okay.
No.
Is the result to start time, end time, or is it entire utterance?
No. You have to say which utterance or which file it comes from, and start time, end time where it comes from.
With a detection probability and a threshold.
With some score and detection probability and some threshold where you decide. Yes.
So I'm still slightly confused. So for the development, when they're doing their development, they have some way of determining how well they're doing?
Yes, definitely, because you have ground truth, but only. You have only where your query appears. You don't know what word is that, and you don't know anything. You just know this query, this dev file appears here.
Yes, but there are only 505 queries.
Yeah. So from that, good luck if you want to get information about what language is spoken. I mean, you can still do things. You can infer things, but.
I can't let it go. So when you say 505 queries, does that mean that there are 505 keywords and there are many more examples of that, or there are only 505 examples?
No, there's 505 keywords, and then there is I think there is between 3 to 4 to several tenths of examples of those keywords in the database.
Okay, so it's pretty small.
Okay, but still, this is like an order of magnitude bigger than last year. So.
No, I understand.
And so anyway, and this, by the way, this we'll see. I mean, you say it's small, but people already complained last year that it was a lot of processing. So that's why. So this is, as I said, a personal objective. These systems have to be fast. Okay, we cannot just do very slow computation and after a week get out. Oh yeah, the query is here. It's not usable. Okay.
Excuse me, Jerry, how long for your template keyword file?
Say it again.
Query term. I mean, give a query term. Query term in your case is a file, right?
It's a file.
How long generally?
How long?
Like how long?
Between I don't know 0.5 to.
1 second or.
Yeah, it's actually. So
the last column, I assume.
Yeah, well, these are averages. Sometimes this means if you look at I didn't explain about the extended def. I don't think it's that interesting. It's just repetitions of some of the queries that we have here. Okay, some of the query we have here, we have several repetitions of the query that participants might use or might not use. So anyway, for these repetitions, they are pretty short. The other queries, some of them are long. So normally it's one word. Sometimes it's two words. So put spoken together. So you have to account that there might be some silence in the middle. But yeah, between 0.4 seconds, I would say, and 2 seconds.
So normally this query file is not completely consistent with the target source, the search file.
You mean acoustically?
Yeah.
No.
Not?
Some of these queries were spoken recorded after the fact. So the database is one database recorded on telephone speech, and then somebody took a microphone and recorded the queries.
Okay.
So it's like all the challenges you might imagine I got in here.
Is it safe to assume that the queries were recorded in isolation, or are they like clipped and trimmed out? And
Some in isolation, some clipped. I mean, yeah, we'll see how this year we can. Last year it was a little more homogeneous. Let's see how this year we can figure out what causes what. Okay, and I think yes. So I'll briefly say this is the typical system that is presented to these evaluations, and we did kind of. We did an analysis of the 2011 and 2012, the main organizers. We analyzed what kind of feature extractors, what kind of normalizations, what kind of matching they were using, and this kind of what came up. In terms of front ends, we can see a whole bunch of things, phonetic probabilities or posteriograms from some models using BTLN, MFCCs, or whatever. The search, you can see mostly lattice or string matching or indexing would fall into this symbol base where you have some knowledge of the language, or at least some similar language, or segmental DTW type algorithms, which is pattern-based algorithms. And then at the decision side, we saw some fusion of systems and some normalization, like they do in Speaker ID, to normalize by the fact that different queries get normally different scores at the end. So you might have a little biased. So we can classify systems normally by the fact that they are pattern-based or lattice-based, or as I like to say, pattern-based, I call them frame-based because it's a frame level that you're matching. And lattice-based, I call them symbol-based because you match at the symbol level. And the data used, some systems used only, we were asking the systems last year. This year we don't ask them, but we asked the system last year to tell us whether they just use the data that was provided, the 2-3 hours that was provided last year, or they use also other sorts of data. And some people tried training their symbol-based systems with some basic phonetic recognizer or some basic ASR with whatever other languages they have, and then try to adapt it. Okay, and this is kind of the explanation I had here, which is basically to say that if they were trying to train, normally train the symbol-based systems, they use either keyword spotting techniques, where you have your keyword and you have some background model and you're basically doing decoding to try to see where your keyword might be, or some string matching techniques using dynamic programming like a symbol-based DTW stuff to find, or lattice or confusion matrix matching techniques to try to find where your symbol query, symbol-based, symbol-represented query appears. And normally to do all this, because of the languages that they had the audio they had to train, where they had the transcriptions is very different from the target languages, they would get some broad phonetic classes, so kind of group classes of phonemes together, so that it's a little closer to what they would expect to find in the language. Okay. Now let's go deeper into the pattern base, which is what my interest lays more. So the pattern base treats the audio as a sequence of n-dimensional real values. No knowledge is used, as I explained already, and we normally use dynamic time warping type kind of algorithms. And just here is just a slide, this funny slide of comparing dynamic time warping to ASR. It's basically, I would like to point out that accuracy in dynamic time warping is not as high as when you know your corpus or you know your language, of course. Now, dynamic time warping, you have a start point, you have an end point, and you're matching two sequences optimally. You find the optimal warping path that matches two sequences. Okay, this is very nice. You don't need any information about the two patterns. You just define a distance metric and you do the path. But the problem is that the standard dynamic time warping, as was defined way back, only allows you to have a start. You have to know a start and end point. So for this, we need to have a way modify dynamic time warping so that given a query, we find in the query you know that it starts here and ends here, but we don't know where it starts and ends in the reference. So you need to find the point.
Yeah, I guess for me the other difference between DTW and HMM-based stuff is that for DTW you have to define a distance metric, and for HMMs it's implicit, right? You know, basically you have Gaussian mixtures and there's...
It's implicit because you're using likelihood to the Gaussian, so...
Right, exactly.
Yeah.
But if you have lots of mixtures and so on, it's pretty general kind of distance, right? So did you just use Euclidean distance?
No, I have a slide with that. Because we are using posterior probabilities, we are using just a dot product sort of distance. But you were using MFCCs, you use Euclidean distance. Yeah, I'll get into that. So okay. So this is just to make you see that if you don't want to have any information about where the start and end of your query in the reference data appears, there is several algorithms already from like 2006, even a little earlier with music. There's several algorithms proposed to try to find with this matching where it appears, right? There's two here. This I proposed 3 years ago, and this one it's the one that's it's going to appear in interspeech finally, and that I'm going to talk about later. So these algorithms, I would like to point out mine. I tried to, and this one here from John Hopkins, Aaron Jansen. We are trying to have an algorithm that is scalable, that is the fastest possible. The other ones are very exhaustive. It's kind of mostly the first one is the first that appeared. They have written many papers, but it's very computationally intensive. Okay, and to make it scalable, several possibilities. Doing a coarse to fine approximation, doing some intelligent boundings of the standard DTW, trying to, this guy here, Imon Keok, he's from Southern California, I think Irvine or somewhere. He does a lot of machine learning, doesn't do speech, but he claims that he's very, very fast, and it's not really, what he does is not really translatable to speech, but it's interesting. He's able to run on millions and millions of sequences, but he needs to know start and end times. He cannot just find the sequence, okay? But within that, he can warp and everything. Now, let's go into the IRDTW algorithm. I call it information retrieval based dynamic time warping. I don't know why, I just appeared one day and it's just, it sounded nice to put together information retrieval and DTW together, even though some people say, oh, this is not really...
You should get one bottle, that's good.
Yeah. So it originates the idea from, I would say this is the most standard way to do a DTW where you don't have the start and end points in the reference. I didn't find references of it except for a book from Muller, Maynard Muller, on explaining it, but I don't know if it's just infused science that people know or that they just all took it from here, whatever. The differences with this algorithm, and we'll see them afterwards, I use a sparse matching, just keep the idea, and I use an indexing structure of the reference data, okay? So, just as a review, subsequence DTW, as Muller defines as is normally used, you have a query term, and you want to find in the first frame of the query some matching sequence that goes from the first frame to the last frame of the query, whatever in the reference data you want to have. So you can start whatever you want here. The insertion penalty on the query is on the reference is 0, and you can end whatever you want on the top hand. To do that, you normally don't define any global constraints, saying normally in DTW you would define these tubular constraints to reduce computation. You let it go wherever you want, and you can use standard local constraints, which basically, if you imagine the grid from before, these are points in the grid, and given a point, you can have paths that come from these directions, or you can have other constraints. I mean, doesn't matter. With that, you do dynamic programming, you apply it to every single point in this grid, find what's the best paths going into it. This is, I always think about this kind of a two-dimensional Viterbi kind of stuff. And finally, you can find what the best path is by looking at which one of these values up here is minimized or maximized, depending on your distance. Here, the distance. Features. I use posterior and features. This is posterior probabilities. We normally just get MFCC 39, then build some Gaussian mixture model and get posterior probabilities of the Gaussians. So we get a 64 or 128 dimensional vector, posterior probabilities of how these features fit in this vector. This is, I didn't invent this. This was shown that it kind of takes away some of the speaker dependency. So it kind of gets speaker independent, even though I think there is a lot to do in here. And I'm looking lately at deep neural networks to do this kind of stuff, but still.
Or just using divergence. So you've got two probability vectors. You know.
Using divergence, okay.
It's expensive.
Distribution.
It's expensive.
And the distance is just a normal cosinus distance, but we put a minus log. So we have a distance instead of a similarity. Okay. Now we have so from the subsequent DTW I just showed before to the information retrieval dynamic time warping, we need to do several steps. The first step is the indexing of the reference data. So this is I actually started the whole thing thinking that I needed to have this. So the rest kind of comes after I decided, okay, I'm going to have the data. If I have many hours of data, the standard DTW has to search exhaustively through all the data. I just wanted it to be somehow indexed in some structure. I didn't care what. In this case, right now I'm doing a k-means hierarchical clustering, but it could be anything else. You can see there is actually, so the second paper about it came before the first paper. This is in ICASP this year, about how we do this clustering and how we use this data, this clustered data to do the search, and I'll have a slide later on. And we use some fast k-means implementation from some guy at Google that works pretty well for this task. So it clusters the data very well. Now, the second thing we do is a similarity matrix. This is what you would have to compute, similarity of all points in the query with all points in the reference to find the matchings. And then within this matrix, you would do the dynamic programming to find your paths. Okay, and I'm sorry that it doesn't look very nice in here. You don't really see paths. There is a couple paths, one here and one here. But anyway, instead of using this whole matrix, now I have this index data and I do queries on the index data and I just retrieve the frames and the positions in the reference that are closest, or the distance is smaller to my query, to every one of my query frames. So that translates to something like this, where the white areas, I didn't compute anything, I didn't get anything, only the colored areas are the distances that I have, okay? So now instead of searching over here, I search over here, okay?
How did you actually index that? Because that's basically a nearest neighbor problem.
Yeah.
So how did you, what data structure did you use for doing that search?
You mean the k-means hierarchical? Yeah.
Well, no, but so out of the k-means, what do you get? Is it an octree or? It's
a hierarchical tree, like different nodes with the different leaves. I don't know, yeah, standard tree, and in the bottom leaves they have the buckets with the bunch of frames from the reference.
Right, because you could. It doesn't matter.
No, we can talk later. I mean, I'm interested in any improvement to that. As I said, this is just one approach. I mean,
it's probably not computationally expensive to do the lookup. So doing that more efficiently wouldn't be that helpful.
Doing that more efficiently? What more efficiently?
The lookup.
Is each node of the tree a reference?
At the final leaf of the tree, there is a bunch of reference points that fall into that category, or into that acoustic similarity. Okay.
At the non-terminal nodes.
At the non-terminal nodes, there is the centroids of the k-means for that particular. I don't know if that's clear.
So what's the centroid of a sequence?
Don't consider sequence. This is back of frames.
Bag of frames.
Back of frames is just cluster acoustically the back of frames of your whole search data. Okay. But I mean, any improvement to that, I'm actually interested
Well, again,
in improving.
I suspect it's not computationally expensive to do the lookup.
To do the lookup is very fast. Yeah.
So it doesn't matter. I mean, I'm thinking about lookup.
Okay.
So.
Now, that's the other thing. The other thing I wanted to improve is the memory requirements. So having this whole matrix in memory, and if X is very, very big, if you have a lot of data, it's huge. It's n times m. So I didn't want to have that. And one first approach I took is what I'm presenting actually this week, is to reduce this search by having a sliding window and having these two vectors and doing a local search. Okay, and this is some algorithm I call memory efficient subsequence dynamic time warping. Nothing fancy, but just it helps with the memory. But this was not the end of it, because I'm still performing an exhaustive search over the database, and I cannot use the indexing I was creating. So this is a possibility, but the second possibility, and that's where the IR comes from, is from some time ago I was doing some algorithms in video in the IR community, and they have this algorithm that I liked a lot, which basically they have you have a query, you have a reference, and you're looking for matches between query and references that are totally diagonal. What happens when you're looking for totally diagonal matches? If you take the subtraction between the query time and the reference time, it's constant across the whole diagonal. So you can represent this matrix into a vector and just see where this t sub k minus t sub r or t sub r minus t sub k, it gets to a peak. And those are your matches. So this
Of transforms or
that's what they call it in image processing. Okay, but these guys don't call it that way. So it's kind of a different way. Half transform, yeah, you would just do matrix computation. This is, you can do it in other ways. But anyway, it's the same idea. Okay, so having this idea, but this is a problem because this doesn't allow you to do warping. Okay, this is just diagonal lines, boom. But it is very nice memory-wise, because you don't need to have the whole matrix. You just need to have this vector, and then in each location of this vector, this is actually a structure. You can store in here information about where each of these little paths started and where they finished. Okay, so with that you can use it very well. And I'll speed up a little because I don't want it to keep you here long. This is the algorithm I'm doing. Okay, the information retrieval dynamic time warping. We do a single forward pass over the query. So look at every frame of the query, one pass, and then after that we can see all the results. The first step we do is a frame matching step. So we go to this hierarchical k-means and we look for the set of matching frames in the reference that match the query. The second thing is, with all these frames, we keep putting them into a system. I'll show you this. It's this structure, this vectoral structure I talked before, to find matching sequences. Okay, and then finally we retrieve all those matching sequences that are long enough, or that are good enough, and those are our matches. So first of all, this is our hierarchical tree. We just go transverse the tree and find for every query frame, we find the set of reference data points. So our bucket of data points that is matching that query. Okay, forget about it's just we have some distance to find. Sorry?
You always go to the bottom of the tree?
Yes. Yeah, not until only at the bottom we have the frames. In the intermediate stages we have just the centroids of this.
Right.
Sorry?
So it's the leaves of the tree have individual frames.
Yes, have the individual frames, or well, the ID to the individual frames. And here there is I'm working with this to try to store the least information possible. So I'm working to see whether I can just have IDs and don't have the actual frame, or I need to have the actual frame. Right now it looks like I have to have the actual frame to have a nice distance to the point. But anyway, this might change.
And what is the width thing you're talking about?
Well, so I wanted to skip this in terms of this is the way I do the distance to each of the nodes. it's kind of, I look at it, the node has, each of these clusters has a center and has a width that's kind of the maximum distance to any of the points that belongs to that cluster. And this is a way to compute, to take this width into account together with my threshold, my frame threshold, to see how close my point would be to that cluster. Anyway, it's just a fancy way of doing a distance to the center. And
so he doesn't have to keep a standard deviation matrix.
Yeah.
Yeah.
So this is the mother of all things here. This is my structure, which is 1D, one-dimensional, not two-dimensional. That's what makes my algorithm be very memory efficient. In here, we basically, each position in this structure is, as we saw before, it's represented by, it points to the place where the difference between the time on the query and the time on the reference is. Okay, Morgan likes the thing. I see you smiling. Okay, any feedback is welcome. Now, in each of these positions, I'm storing a set of information, storing the start and end points, start and end times in the query, start and end times in the reference that match in that location, accumulated distance and number of points matching in that position. This is all I'm storing. I'm not storing any particular frames matching or anything. Okay, it's very small amount of information. Let's see. And so, how do I store things there and what do I store? Okay, so this is an example of what we would do in standard dynamic time warping. In standard dynamic time warping, you have matching paths. These ugly paths are matching paths that come in the matrix, boom, 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 and they get to each one of these 3 points, and then for a given new point, I select which one of these 3 paths is my best path. Okay, this is a standard. So instead of that, now what we have a problem. We have sparse matrix. So we might not have paths right next to us, but they might be a little farther away, right? So we might have paths over here, but they are here just because there is nothing from here to here, okay? Or there might be a little that way, more than diagonal, whatever. So what I do is I define some constraints, and there is a constraint on the width, or you know, where do I look? This is equivalent to my local constraints in the dynamic time warping. Okay, and then there is a constraint on how far my paths are. So defined by this and by these dimensions. Okay, so according to these constraints, this path here cannot be matching to this point. These 2 paths here can be matching to the point only if we consider this, let's say, basic warping constraint. If we consider a constraint like this, which would say that a query can only match up to twice the size, twice the speed, or half the speed of the reference. So we would only consider these 3 paths here. Okay. So looking into this, we can define a set of variables we'll use afterwards. One of them, well, the variable we define here is the wide range, is the width range, which in the case of 2x warping, it would be this size here, and the x, in that case of the standard basic warping, would be this thing or this thing. Okay. So how do we use that? So this would be the matrix representation. But as I said, I'm not using matrix here. I'm doing everything in that vector. So how do we represent this kind of intuition here of these paths in the 2D into a 1D space? So doing a little bit of thinking, a little bit of algebra, you can see that if you have your delta t minus, so time of query minus time of reference points to this position, you can collapse all those paths that are in your warping region to either paths that are here or paths that are here, depending on, you know, either your full warping or so standard warping or 2x warping. Okay, so only these paths for a given point, for a point in a matching point, which is a query frame and a reference frame, only the paths in this region should be considered. So you don't have to look at the whole vector to see who can get to your point. Moreover, if you apply the constraints of the basic warping or 2x warping, within here, only those paths that have, so if you see here, this is a point, this is the last point of the path, this is your new query reference point. You can define this delta r and this delta q, so variation in reference and variation in time in query. So only the ones that have delta Q better than 0, delta R better than 0, or delta Q greater than delta R divided by 2 and the other way around, only those from those that are in here should be considered. Okay? So now, we've constrained a lot, and we can do this search kind of fast, because we're looking just at a few paths around the points, and from those, taking out all those that don't accomplish this. But you still, yes?
So what is the average estimation of that vector?
It's a good question. The dimension of the vector should be the size of your query plus the size of your reference, because you have to consider all the possible one minus the other combinations, okay? Now, this, in theory, can be very long, but I was thinking, okay, if I want to do a memory efficient system, I cannot have just this just explode on me. So you can basically, and I implemented that and tried that, you can basically do a circular buffer with that, and just have okay, maximum I want to have 2 megs of this vector, and anything that goes outside, it just comes at the beginning. You just have to keep track of, bookkeeping of who's who and where it comes from. So you have all these vectors. So now imagine these 3 vectors are the good ones, okay? So only one of them will connect to this point, only one, which means only one will be registered in that position in the vector. So which one do we use? And this is the trickiest part I had, because in dynamic time warping, when you have sparse matrices and it's not a standard, you cannot just use a score. You just would say, okay, the biggest score at standard DTW, you use the best, the one with the best score. In here, you have to put the distance also. Like very, very, very small paths of 1 or 2 points might have very good score, but they are not useful. Yeah, and very, very long paths might have a very bad score. So if you only use the length, they might not be useful. So we have a cost metric that uses the distance, accumulated distance, together with matches to come up with a comparison distance. Okay, and after that, we selected, okay, the path that is here, because this is the paths live in each of these cells. The path that is here, after this step, comes in here, is registered in here, okay? Once we register in here, we just have to update the information. The endpoints change because we have the new endpoint. Accumulated distance is added the new distance, the number of matches increases. That's it, okay? Now, let me just have a couple of minutes. This is my whole system. Nothing really fancy. I explained to you this part here. Okay, and this is feature extraction. I get posteriograms from here, some voice activity detection, because in silence regions all the matching gets a little fuzzy and doesn't work very well, and at the end some overlap detection to eliminate paths that are very on top of each other. Okay, I'll skip all these slides, and I'll just mention that now, instead of having matches that go from here to here, normally you have matches like this. So you get portions of this matrix that match. But of course, we want to, in this particular application, we want to have a match that goes from here to here. So as a little hack, and the guy in Johns Hopkins also does the same basically, as a little hack, we project this thing and we compute a real distance using a local standard subsequence DTW in that area. Okay, so it's kind of a little overhead, but it's very localized and it's very fast. Now, well, in terms of performances, we use the standard NIST metrics. I use also memory usage, of course, and real-time speed. Okay, I'll just show you. In terms of memory, this would be a standard DTW or a standard subsequence DTW. This is in terms. These are 10 queries, and this is the African data set is 3 hours. So if you put this, each of the queries, it needs to create the matrix. At the top of the matrix, it depends on how big the query is. It will take more or it will take less memory. This is in megs, so it goes up to some 1 gig and something. And this is the IR DTW. It grows a little bit because you have to register the matching paths in that vector. But we actually, some of those paths in the middle of the process, you can already erase them because they are not useful. They are totally obsolete. So you do some memory keeping, and it keeps very low. Okay. And real-time factor, this is something I still I still want to see more improvement. I'm still not happy with. And I'll just show you. Yes?
Oh, I just wanted to look at 2 seconds here.
Yes, sure. Okay, so this is from a paper we did last year. This is the paper that we published in ICASP, and this is basically numbers for a Python implementation. Okay, it's not that the Python implementation is much slower, and the C implementation, this one here, which would be the fastest, I just finished implementing it right now. So this one would be very fast, but this is estimated. Okay, this is projection. So all these other ones, these two are real. So okay, the way I compute this, okay, you should know, is the time I take to find the query in the database divided by the size of the query, so the time the query takes, so it normalizes to 1 second, finding 1 second, and divided by the total time of the database. So it's a comparison of how much faster I would do if I would listen to the whole database myself to find the 1 second query. That's basically how it is. Okay, and still I think we should go faster than this to have systems that are really feasible. Okay, and to finish up, I'll just show you a few example plots for you to get the idea. So let me play the reference. I don't see where I'm at. Oops. No.
There you go.
Okay, this is the query. This is one of African languages, and this is the reference. Sorry, and this is the query. So this is a woman saying Nyabonga, and the man said Nyabonga over here and over here. Okay, and this is the 5 best result of the subsequence DTW. 5 best because you won't see it, but there is 2 results here, one in high overlap and 2 results here, and there is another result. The first 2 results are actually the real results. This would be a similarity matrix with the standard threshold I'm using. Which matching frames you would get. If you use a more restrictive threshold, you would have much less of them. The matches are still over here and over here. I mean, at naked eye you don't see it, but the algorithm does find them. So this is basically the results, and it's not see much here. I have to change the colors. You see here these like little lines here, over here, over here, over here. So this is kind of, I call them the worms. You get the worms all over your matrix, and the 2 ones that are interesting is this one here that goes from here to here, and this one here that goes from here to here. Funnily enough, the start and the end of the query is because in the reference it's within context, and in the query is no context, so it's different enough that it doesn't find it. So it just finds the central part, and that's basically it. I mean.
So you have the reference backwards from the way you would normally do it, because usually you have the 10 going up.
Right.
You have it going up. I always have it going down.
Yeah.
Sorry for that. I always do going down. This is how MATLAB plots it. So whatever. I mean, so here's a link to the. So there is the IRDTW Python code is available. It's very slow. It doesn't really make how to say it, it's not a really good example of how this can do. I mean, actually, I'll soon put the latest version I have, which is a little better, because the first version we put up, it was not very memory efficient, because the way Python manages memory is horrible. But it's a good indication of how this algorithm can work, and it's easy to understand. It's actually very nicely implemented. And I'll present this in interspeech, and right now I'm looking to how to implement. So for the IRDTW is a very interesting concept, because it's a sparse matching. So it's basically you're looking for some warping between points that are far away from each other, and that gives me a lot of game. I can play with it a lot to do interesting stuff. And so I'm starting to play with symbol-based matching. So doing lattice-based matching using the IRDTW, and similar things with DNA, but still no results. So that's it. Thanks.
guess it's probably just something I'm not understanding. One thing I was confused by is later you do all these sparse things which get down in computation, but you still have to look at every point in there to see which things should be included in the
every point of the remaining points that I have. Yes.
Yeah.
The idea is the indexing cuts down the number of points I look at a lot.
No, but initially, to figure out how to index, you have to compare every point in the...
Yeah, but that's in the kind of that's offline, right? Do you mean to build the KD tree, to build the...
He does that beforehand, before he even knows what the query terms are.
To build the k-means tree, you mean?
No, I mean, you get a query term, and I thought that in order to figure out what the sparse things are, I thought you had to compare every point in the query to every point in the reference point.
No. You get once you get the query, for each point in the query, you go to the tree, to the k-means tree, transverse it, and then you get a list of references. And then, with those, you need to do the processing with each of them. Okay, so I have to see how.
I see. So the K, right? Okay, I didn't get that. The k-means tree is developed before we see the queries.
Yes.
Okay.
Yes. Okay.
Gotcha.
It's I would say people say it's old technology, but I think it still has some potential, and if no information of the language is there, I think
Fire still works.
Sorry?
I said Fire still works, and it's really old.
Yeah, well, so...
You'd think that sort of the original idea of sparse, compressed sensing, that you'd think that, or I would think that would actually be related to what you're trying to do.
I should look it up. Yes, compressed sensing, you say?
Yeah, I mean, when Donahoe and his colleague did this, they were working on an image sort of restoration, I guess. And it's a very similar sort of problem, trying to find underlying structure. But it may be that I'm just totally wrong. But if you could find a sparse representation, using what they did, you might get a sort of smoother estimate.
Mm-hmm.
I mean, it might not help you, but see, what's funny now is the sort of pre-indexing that you do, if you want to call it that, this sort of look ahead or whatever, is point-wise, and it takes into no account time.
Totally, yes.
And you'd think that by taking into account time somehow, you could, and the structure, you might get a win somehow. But I mean, I may be totally wrong. Maybe it's just
no, definitely. I mean,
time work.
One of the things I have in my to-do list is actually to look at other ways to index the reference, but it's in the to-do. So
the k-means thing is basically quantization, right? So you're just mapping whatever the input space is to some concrete dimensions, right?
Yes.
So you could just extend that to temporal structures, right?
Yeah.
You don't have to change anything.
That would be one way. That also get some meta features out of there and cluster them, or The only problem, I mean, I don't know, spectral clustering. There is other clustering techniques, but this becomes a lot of points to cluster, and we found this k-means algorithm that works pretty nice, and it's pretty fast even with large number of points. So
why don't you use a deep network with a bottleneck?
That's what I said. I'm trying that. I still haven't gotten to. So at least, and Morgan here might have some insight. At least what's advertised in all the papers is that the deep neural network gets the structure of your data, and each layer gets a higher level structure of your data. So in theory, if you get that, and then the last layer you condense and you have these posteriors equivalent there, in theory that should give me something that is.
Deep neural nets are just multi-layer perceptrons.
I know.
And some of them have more layers. Some of them don't. Some of them use pre-training. Some of them don't. And if you get better posteriors, that's good. I mean, the other thing I was saying before is, I mean, the way that we train them is using the cross entropy criterion, which is basically comparing a target to the output.
Mm-hmm.
You can do the same thing with comparing two. And that's what I was saying before about using divergence or something like that. You know, you're comparing two examples of a distribution.
But what would the targets be to start with?
You could do an auto-encoding.
Yeah, an auto-encoding.
And then just use the bottlenecks or the dimensionality reduction.
But
you're getting posteriors now, right? So
Yeah.
how are you doing that?
I'm thinking more of the DBNs as a way to get posteriors, as I get to get the feature.
But right now, you're using some of those, right? So what do you use for your targets since you don't have light?
He just does
It's a GMM.
Yeah. To get the posteriors, yeah, just the CMM.
Oh, you're just using.
I use a weird GMM.
I see.
In ways, it's not a maximum likelihood GMM because I use some k-means in there, but
I see.
I use a GMM.
Sean, quick question. Have you, if you think in terms of algorithmic complexity, in terms of big O notation, right, like the SDTW, if you say the query is of length n, the reference is length n, and I think it's m squared. Is that right?
Yeah, I don't know my case.
You know for IRDW?
I'm a double E. I don't know about big O.
But I'm just saying, in theory, it should be less than that.
I hope so. But I mean, I think the most gain it comes from the indexing, from the fact that I don't need to process each point. But and I'm getting very fast implementations. But yeah, someday I have to check. Sit down with some.
It'd be good to know if in theory you should be able to do faster. It's just a coding issue.
So as I said, the only person that does something that is very scalable is at Johns Hopkins, but that they do half transform as a first step to get a diagonal estimate of where there could be a match, and then they do a standard subsequence DTW on that location to find the exact defined stuff. And
you said somebody at USC.
And then they use LSH as an indexing for the data. But
projected to Euclidean space.
Yeah, but the way that they search for it. Oops, I'm being recorded now, right? It's I'm not that fond of it, so that's why I didn't use LSH for my stuff. I used the k-means, which I think is better to transverse, and you get a better final buckets of reference.
For this eval, does processing time matter?
For the 2013 is one of the metrics we ask people to report, because like last year we got very good results, but some of those systems were very slow, and I think it's at the end of the day, if you want to have a real system, you have to think about everything. So, but we'll see. I will see. I mean, we have 18 people registered. We'll see how many finish the line.
Thank you.
Thank you.